in this module I will be discussing on that dental glass ceramics materials. Now, this glass ceramics is essentially defined as the materials which contains crystalline ceramic phase in an amorphous glass matrix. In an amorphous glass matrix. Now, one of the things that I will be doing in this module is that first I will briefly introduce to that dental implant systems to start with, and then I will discuss rest part of this module only on the processing and properties of some of the machinable glass ceramics. Now, why machinable glass ceramics? That machinable glass ceramics essentially means that because of the presence of certain crystalline morphology in the glass matrix, these materials you can get them in the machine to any particular shape using a CAD/CAM based technique like conventional computer aided design and computer aided manufacturing based techniques. So, this will expand the application of these machinable glass ceramics to a larger extent. So, this is the cross section of a tooth. So, what you see, the bottom part is the root of the tooth. Now, you have a dentine here, and in the top part is the enamel. So, enamel is the part where you have that harder phase or harder enamel or harder calcium rich phase is there, and this top part is totally crown. So, structurally you see that the tooth is made of the crown and the root part, and you have a root canal here. So, in the one of the commonly used clinical therapy is a root canal therapy RCT, which is done quite often, and you have a cementum here, and you have a pulp cavity in this part, that which is indicated by this arrow. Now, this dental glass ceramics which can be used in this particular case and which will be discussed in this particular module, that can be used to make the crown part of the tooth. The root part or the titanium implant essentially, that can go inside the damaged tooth part to replace the damaged tooth, and on the top of it you have to put the crown part. So, this is the typical ceramic crown. As I said, that as you can see that ceramic crown, why it is so attractive in case of the dental application, simply because ceramic crown has better mechanical properties, and also ceramic crown has longer durability, and it has good aesthetic appeal as well. Now, this rest of this module I will discuss about this development, processing and properties of that machinable glass ceramic materials. So, some of these machinable glass ceramic materials are currently commercially available, and that means it is produced by some of the companies internationally, and some of the brand and trade names on which these machinable glass ceramics are available, they are like Macor glass ceramics, Dicor glass ceramics, Vitronit and Photoville. Now, all these glass ceramics are characterized or can be distinguished from one another by two things. One is the composition of the crystals or ceramic phase that is forming, and second one, the morphology of the crystals or morphology of the ceramic crystals that are present in the glass matrix. Now, why I am stressing too much on the morphology of the ceramic crystals? Because the morphology depends on what are the kind of heat treatments that you are giving to this particular glass matrix, and because of this heat treatment you can essentially tune the glass ceramic composition that is being nucleated in the glass matrix, and also that their morphology, that is also you can have some control. So, this is the SM image just to show crystal growth of mica glass ceramics, a mica in the glass ceramics diffusion control, and this is published in way back in 1991, almost like 25 years ago, in Journal of Non-Crystalline Solids. Now, what are the properties of the mica based glass ceramics? That is good machinability, they are strong, there is thermal shock resistance, and these are good excellent dielectric properties and so on. Now, as I said that it has a very characteristic crystal morphology, and you can see that is a network of the potassium, fluorine, magnesium ions, they are present in a particular tetrahedral arrangement as well as very characteristic crystal morphological features, when these crystals are viewed along 001 directions. Now, what is the reason for this machinability? Now, suppose you have a straw like crystals in the materials, this is like a straw like crystals in the material, this is that, and the straw like crystals are essentially anisotropic crystals. Now, the moment a crack comes, now crack cannot go straight away to the other surface, to the other face of the materials. And these, if you have a very weak interface, then when the crack comes, as has been shown here, crack now can be branched or they can be blunted. Now, when it comes and blunted, then it can go to the other surface only after deflection through the boundary of these anisotropic crystals. And these anisotropic crystals, since it is also brittle because it is ceramic, they can break or they can fracture at any specific part of the crystal and in a very random manner, and then after that this crack can find its path, can find its original path, because crack always have a tendency to trace back its original path of propagation, so that it continue to propagate in the unaltered direction through the glass matrix. So, this is what has been shown here in a very schematic manner. So, the more is the resistance to the crack propagation through the specific crystal arrangement in this glass matrix, the more better will be the machinability. Now, if a material can be fractured very easily by the propagation of the cracks, you cannot give it a particular shape to this material, simply because you do not have any control over the way this crack will propagate through this through this microstructure. Now, to substantiate my statement, what I have made like few minutes ago, that indeed it is possible through that heat treatment procedure that you can have different crystal morphology. They are distributed in different manner in this glass ceramic materials, and this has been shown here. This is in the case of fluorophlogoperide based mica based glass ceramics. The first stage, as it has been shown, that is a phase separation. Phase separation means that is prior to the nucleation of the crystals. Now, when you heat treat this material at 640 to 750 degrees Celsius, you form the chondrodite phase, that it has a different structural features, and then which changes to norvegite when it is heat treated at 750 to 850 degrees Celsius. Finally, when you heat treat it in the temperature range of the 850 to 1100 degrees Celsius, you get more equilibrium fluorophlogoperide phase with a characteristic straw shaped crystal morphology here. And what is the equilibrium composition here? You get KAlSi2O6 plus magnesium silicate and magnesium fluoride based composites. Now, in one of our recent work, we have observed that depending on what is the composition of the base glass, you can indeed actually have a control on this the morphology of the glass ceramics. So, the straw shaped morphology were obtained from the same glass composition, which is heat treated at 1040 degrees Celsius for 4 hours. But if you do the heat treatment for longer time period from the same glass at 1000 degrees Celsius for 24 hours, we see what we call butterfly shaped. So, this is the nucleation point, and then all the crystals, they are kind of very nicely and in a very unique manner, they are growing in different directions, giving it to a butterfly shaped. Another shape which is also reported in literature, but to a different glass matrix, what they call cabbage shaped crystals. Now, these cabbage shaped crystals, certainly you see that there are a lot of concentric rings like onion, and these concentric rings, it is forms a position in a very dense manner in a glass matrix, and which is indeed different in terms of morphology compared to when you compare to a straw shaped crystals. Then also people have reported star shaped crystals like Na2O, 3.2 K2 and all these things, and also aligned crystals, like you can see very well aligned manner these crystals are formed in this particular material. Now, coming to that this case study, which is again based on a published work, and this is based on the MTech thesis work of two of my former students from IIT Kanpur, one is Atiyar Molla and one is Shiban Rai, and this material is based on SiO2, Al2O3, magnesium oxide, K2O, B2O3 and little bit of fluorine also being incorporated through the use of ammonium fluoride as a precursor. So, essentially all these powders as well as their precursors are added in a specific ratio in a different kind of glass composition just to vary the fluorine content, and fluorine content is varied over 1 to 4%. In this narrow window we are seeing that how fluorine content can give rise to glass ceramic materials with different morphology A and B with different properties, both physical and biocompatibility properties. I repeat once again, this is a silica based glass, but other element or this is silica based multi component glass materials, but with other compositions they are mostly oxide based like alumina, magnesium oxide, K2 and B2O3, and the fluorine has been incorporated in this glass ceramics through the use of the ammonium fluoride as a precursor. Now, how these glass materials are being processed, that is very important to note here. So, essentially all these oxides are mixed initially. After they are mixed using the ball milling technique, then they are simply melted at a temperature of 1550 degrees for 2 hours in a conventional sintering furnace. Then once it is melted, this melting experiment or melting is to be done in a platinum crucible. Why platinum crucible? If you do it in the alumina can sustain 1600 very easily, but then there will be pickup of the alumina from the crucible itself in the glass matrix. So, that actual balance of the different oxides which you have done initially at the design of the glass composition itself, that will be disturbed. In other words, what I am trying to say is that if you use alumina crucibles to melt this particular glass ceramic composition or glass composition, what will happen? You have alumina in the base glass, right. Now, if this composition is now melted in a alumina crucibles, then what will happen? There will be additional alumina pickup from the alumina crucible. So, that this targeted composition or this initial composition will not be same the way you are showing in the table. So, it will be disturbed. So, in order to avoid this kind of pickup or contamination from the crucible, the platinum crucible, which is very inert and which can also sustain high temperature, that is to be used for the glass melting, and that is used worldwide in most of the laboratories who prepares the glass. Then after that you just simply quench the glass in water and to prepare the glass feed, and the glass feed means there is chunks of the glass that will be that you will get. Then you grind it and then you do it additional melting. Why this additional melting is required? Because just to observe, and let me emphasize it again, it is a multi component oxide based glass. Okay? So, it has not only silica, but alumina, magnesia, potassium oxide and boric acid or boron oxide is also there, and their amount is not negligible, it is a large amount. This homogeneous mixing of all these oxides require not only one melting, but also multiple melting, so that these materials are very homogeneously mixed. After you do these things, then you cast this glass melt in a usable form, and after that you anneal this glass at different temperature like 610 degrees Celsius. You do these things, and then after that you do ceramization of the glass. What is ceramization? Ceramization is the heat treatment procedure which will enable the nucleation and growth of the ceramic phase in the glass matrix. So, ceramization essentially a heat treatment to facilitate nucleation and growth of ceramic phase of crystalline ceramic phase in glass matrix. And ceramization process actually takes place at a temperature much lower than the melting temperature of the glass, but reasonably high enough so that there is enough driving force for the nucleation and growth of the crystalline ceramics is there in that in the glass matrix. Now, to illustrate further, that ceramization process in this particular case was carried out at different temperature of 1000 degrees Celsius to 1120 degrees Celsius by holding the glass glass at this different temperature for 12 hours. Now, depending on what is the temperature that you are holding it for 12 hours, what you see that initially the glass has a very large hump, and this hump essentially is characteristic of any amorphous material, like it does not have any sharp peak, but rather a very broad hump kind of things, and this shows that disordered or glass peak. Now, when you crystallize them or ceramize them at 1000 degrees Celsius, you see that this all these characteristic fluorophagopite peak, which is rather sharp, and that is shows that crystalline fluorophagopite that is starts appearing. And with higher and higher temperature holding at 1040 or 1080 and 1120, this peak, their intensity increases to many extent, and also their sharpness of the peak also increases. That means they are becoming more and more crystallized. So, this is in the case of the M1 glass composition. In case of M2 glass composition also we have seen that similar fluorophagopite based. So, it is monophasic glass ceramic materials. Initially base glass is amorphous, and then all other characteristic fluorophagopite peaks appear at higher sintering temperature. Now, in terms of morphology, what we see that these mica straw like crystals, they are forming not only in one direction, but also in different direction, depending on whether these materials are crystallized or ceramized at 1000 degrees Celsius for 24 hours. Interesting enough, when these materials were ceramized at 24 hours at 1060 degrees Celsius, what I describe this morphology as like envelope like crystals. This like postal envelope, so it is like envelope like crystals, and these crystals essentially have 4 different domain, and each domain the straw like crystals are oriented in a particular orientation, and this orientation differs, and this orientation there is a clear transition at the domain boundary, which is shown here in the dotted line. So, this kind of morphology is indeed different from what I have described in earlier slides, where I have shown cabbage shaped crystalline morphology or star shaped morphology. Compared to that, this is indeed a different. The other interesting things that you notice here, this stacking of this crystalline or rod shaped morphology, it is indeed very dense. So, it is not like in the same way that you have seen that which are dispersed in the microstructure, but it is very dense straw like morphology, but in a very dense manner, and this kind of dense arrangement of these crystals in the glass matrix would essentially give rise to better mechanical properties, which we will see in some of the next slides. But this morphology is certainly sensitive to the composition of the base glass, the way you are choosing, like you go from M1 to M2, and M2 as cast means without ceramization. So, without ceramization you see that this material, these crystals are also have different morphology, and then once you start crystallizing, then you see the different type of crystal formation, but these crystals does not have any specific morphology or very regular morphology, the way you see, the way you have seen in the earlier. Now, in terms of hardness of these materials, now this blue ones is the hardness. What you see, these materials has a hardness of 8 gigapascal. Just to give you the relevance of this value of 8 gigapascal, the steel material, which is when hardened in the fully martensite conditions, they have a hardness of 7 gigapascal. Now, compared to fully hardened steel, this glass ceramic has almost equal or identical hardness like 8 gigapascal, which is extremely hard, and this extremely high hardness can be attributed to the specific crystal morphology that I have described to you a few minutes back, and which I described as the envelope like crystal. So, those type of characteristic crystal morphology is helpful to get that hardness values are so high, more than 7 gigapascal. And what is the crystal volume fraction? That is up to 60% volume fraction of the crystal, which is also indeed very large number. So, essentially by varying the base glass composition, the crystal volume fraction varies in the window of 60 to 70%, and hardness value varies in the range of 4 to 8 gigapascal. So, another interesting thing is that normally one can assume that if you plot the volume fraction of the crystal volume fraction of the ceramic phase in the glass matrix, and if you plot the hardness along the y axis, normally one would expect larger the volume fraction of the crystals, more is the hardness values, but that is not observed. This kind of trend is not observed here, simply because here the morphology changes. If you go from M1 to M2 as I have shown you before, and you go to M2 to M3, the morphology, crystal morphology changes, and that because of the change in crystal morphology, that any kind of systematic trend with the increase in the volume fraction of the crystals to an increase in the hardness, that could not be realized in the present case. So, this is that some of the other properties and just a comparison with the commercial macro based glass ceramics. So, that density of that our glass material is 2.8, macro glass is 2.5, flexural strength was 80, macro was 94 MPa, elastic was 69, here it is 67 gigapascal, hardness was 6.4, higher the hardness, better is the wear resistance and better is the durability of these materials. So, our material, that which was the experimental material, I put a star, and why I put a star? Because that really has much better properties than some and than one of the commercially available dental glass ceramic. Now, coming is the in vitro properties. Now, this material does not contain any hydroxyapatite, this material does not contain any calcium oxide, I think it contains calcium oxide. If I go back to this one, it does not contain any calcium oxide. So, this glass ceramic material does not have any precursor material which can facilitate for the formation of the hydroxyapatite formation in the in vitro. But when this material are dissolved or when this material are incubated in a simulated body fluid with some of the precursor solution, what we have seen interestingly, that these nodules are essentially calcium phosphate. This material is calcium phosphate rich phase. Another interesting things that we have seen, that these calcium phosphate rich globular shaped, this is called the process called biomineralization. Why it is called biomineralization? It is called biomineralization simply because that it does not have any calcium phosphate phase here, but it produces calcium phosphate nodules when it is dissolved in vitro in a simulated body fluid solution, and these nodules do not appear immediately after the incubation, but when you incubated this material for 2 weeks, then 3 weeks and up to 6 weeks, then mineralized rich layer form, mineral rich layer forms. So, which essentially shows that this material can make good biological bond with the osseous structure, with the tissue structure. Why? Because your natural bone or hard tissue also is mineralized tissue, right. And so, if you have a mineralized tissue, when they will see on a material surface where there is a mineralized layer formation, automatically there will be better compatibility with the natural osseous structure. So, I hope I have emphasized this point enough so that you understand that it is possible for a material without even containing calcium oxide or some of the precursor of the calcium phosphate rich, but they can indeed form this calcium oxide calcium hydroxyapatite formation when they are dissolved in artificial saliva, for example. Now, artificial saliva has a typical composition of sodium chloride, it is sodium chloride, calcium, potassium chloride, NaH2PO4, Na2S and some urea. So, artificial saliva essentially simulates that oral microenvironment that a dental crown or dental material is expected to experience during application. So, that is why that artificial saliva is to be used for all in vitro studies related to the biomineralization of this material. Okay. Now, coming to the some of that cell level study like in vitro cytocompatibility or bactericidal studies, this is certain neat results that we have obtained and quite encouraging results. So, antimicrobial properties were studied using Staphylococcus epidermidis as one of the bacterial strain, that is gram positive, and their adhesion on the glass ceramic materials were tested after 4 hours of growing them in this Loria growth medium. Now, after 4 hours you do see some Staphylococcus aureus bacteria, but when you compare with that of the control, that bacterial adhesion of the control, this number of bacteria is certainly less. Another thing that we have noticed, that when you have grown sarcoma osteosarcoma cells, that is that one of that osteoblast like cells, it shows a very flattened kind of morphology, and also it shows a very long filopodial extension, and there is a number of these flattened cell morphology you can see here, and also there are indication that is the extracellular matrix like layer formation when the cells have reached the confluence state. This is more clear here, and you can see here that how these filopodial extension and cellular bridge formation they are forming on these materials. Now, in terms of MTT assay of the L929 mouse fibroblast cells, these are the three composition we have tested. One is M1, one is M2, and one is M3, and their days of culture is 2 days, 4 days, and 6 days. Now, what you noticed here in the control M1, M2, and M3, these three type of materials, that L929 cells they grow because that there is a systematic increase in the MTT optical density values. That means the larger the optical density values, more is the number of mitochondrially viable cells. So, when cell grows in an uninterrupted manner, in a very linear manner, that means these glass ceramic materials can be used as a cell growth substrate also. And there are certain statistical significance aspect has been highlighted in this slide, and essentially it shows that with respect to control at different time points in culture, how these glass ceramic materials they have a different statistically significant increase in the optical density. Now, alkaline phosphatase expression or activity is also been quantified on these materials using sarcoma osteosarcoma. So, that is the earliest differentiation marker for the bone cells, and what you see that ALP expression is much higher compared to the control here in the M1 glass, and M2 and M3 they do not support this kind of differentiation of the bone cells. Essentially that M1 is better in terms of that cell level compatibility properties concerned. Now, little bit more details of the antimicrobial property study. So, you have the control here, this is the control, this is the bacterial adhesion on the control sample, that is tissue culture plastic. This is that M1, this is M2, and this is M3. Now, with respect to control, certainly you see that M1, M2, and M3 there is less number of bacteria adhered. The second thing that you notice, M2 and M3, M1 and M3 there is significantly more compared to the control sample. As I said in earlier modules also that in order to establish the antibacterial property, one has to use the 2 bacterial strains, and indeed we have used the 2 bacterial strains. One is the Staphylococcus aureus and this is the one E. coli, Escherichia coli, and Escherichia coli also we have seen less number of bacteria which are growing or which adhered on the material substrate like M1, M2, M3, and particularly M3 is even less number of bacteria are present. This quantification is done using UV visible spectrophotometer, and then what you see here, this is the reading for the control. Now, compared to control M1, M2, M3 there is indeed significant decrease in the optical density values. So, therefore, they show that S. aureus bacteria their growth is inhibited to a large extent on this M1, M2, M3 glass ceramics. So, they not only have antibacterial property, but they also can be used as a good cell growth substrate to facilitate cell viability and cell survival on these materials. So, this brings us to the end of these dental glass ceramic materials. So far I have covered these different case studies just to highlight how to develop materials for different applications including dental material applications, how to design that specific material composition, how to process these materials, different materials, and particularly I have emphasized that in case of dental glass ceramics that this combination of the glass melting, casting and heat treatment that is indeed different from the rest of the ceramic processing which extensively involve either conventional sintering or spark plasma sintering or other advanced sintering techniques. So, this glass melting is also kind of unique in a sense that one time melting is not enough, you have to do multiple melting to ensure homogeneous mixing of the multi component oxides or multi component phases in the glass matrix before one can even start the ceramizing treatment, because ceramizing is one of the treatment which is to be conducted in a uniformly melted glass composition, so that you have that equal potential sites for the nucleation of the ceramic phase. If there is a compositional inhomogeneity in the base glass itself, so therefore, chances of the nucleation of the ceramic phase will be different depending on whether there is a compositional segregation. So, you have to rule out any compositional heterogeneity in your base glass matrix before you start the ceramization, and thereby you ensure that base glass has the equal potential to act as a substrate to nucleate the ceramic phase on these materials when they will experience the heat treatment. And once these crystalline phases are distributed uniformly in this material, then you will have better chances of uniform ceramic phases being crystallized and growing and the glass matrix uniformly. And once you have this total crystalline ceramic phase on these materials and in a very dense manner, then this material is expected to have better mechanical properties also, as well as their in vitro or in vivo biocompatibility. Another things that I have emphasized in this glass ceramics, dental glass ceramics, that it is not important to have hydroxyapatite based hydroxyapatite phase or any precursor phase in the material to induce the biomineralization in the in vitro. Biomineralization means, I repeat, that is the ability of a material to form calcium phosphate rich layer when they are incubated in a physiological environment, be it simulated body fluid or be it artificial saliva. In those kind of physiological environment, if a material is incubated for a sufficiently longer time period, whether the material has the ability to show that it is indeed can support the calcium phosphate rich layer formation. Here in the case of glass ceramics that we have discussed in this module, I have clearly shown when this material is incubated in artificial saliva for sufficiently longer time period up to 6 weeks in the artificial saliva, it can show very distinct calcium phosphate rich globule or very spherical globules in a dense manner. It forms very clearly on the surface, and once this mineralized layer forms, it has a greater acceptability in the body environment, simply because that although this is not a hydroxyapatite rich glass, but it has that hydroxyapatite rich surface phase, and having that hydroxyapatite rich surface phase, it will help in the osseointegration, because your hard tissue or bone natural tissue also is a mineralized tissue. That means, it also contains a hydroxyapatite phase. So, therefore, in order to because they have a compositional similarity, they will have better integration in that osseous system. Thank you.